Okay, then chapter 17, circular motion. These are the objectives of this chapter. Okay, so here are the objectives of this chapter on circular motion. You should be able to convert from radians to degrees. We have something called angular displacement. Okay, and we will express that in radians. So one of the objectives is to be able to convert from radians to degrees. Then also we will see solve problems using the concept of angular velocity. We will see what this is. Okay, for angular velocity we have the symbol omega. I think I told you that there are 24 letters in the Greek alphabet. The last letter is omega. Okay, we have both capital omega and simple omega. Capital omega is the symbol that we use for resistance, the unit of resistance. And here we use the other omega, which is like a W. Okay, so we will see what that is. Then describe motion along a circular path as due to a perpendicular force which causes a centripetal acceleration. Okay, anything moving in a circle is accelerating, even if it is moving with a constant speed, and we call that acceleration centripetal acceleration. That acceleration is directed towards the center of the circular path in which the object is moving. Okay, so this chapter is about circular motion. So for example, just give you one example here. Let's say we have an object that is moving in a circle. Okay, so this is loading. Okay, so if there is an object moving in a circle, something wrong with the pen, I guess. Yeah, we'll leave it some time to load. Okay, then the next one is recall and use equations for centripetal acceleration and for centripetal force. So like F is equal to ma, here also we have some equations for centripetal force and centripetal acceleration. Actually, we are using that equation F is equal to ma, and then getting the equations for centripetal force and centripetal acceleration. All right, so let's say for an example, there is an object that is moving in a circle. Okay, so this is the circular path. Let's say this object is moving here. This is the object and it is moving in a circular path. So if an object is moving in a circular path, then even if it is moving at a constant velocity, there will be a acceleration because the direction is always changing. Okay, the direction is always changing. Now you can see at this, when the object is here, the direction it is moving is this way. So the velocity is this way. And then after some time, let's say the object is here, then the direction of velocity is this way. Let's say then the object is here, then it is moving down. Okay, so at every moment the direction of velocity is changing. So even if the speed is constant, since the direction of velocity is changing, the velocity is changing because velocity is a vector quantity. Vector quantities have both magnitude and direction. The magnitude of velocity is speed. The magnitude of velocity is speed. Okay, so let's say this has a constant velocity of 5 meters per second. Okay, 5 meters per second this way, but since the direction is always changing, the velocity is changing. Now if the velocity is changing, change in velocity is acceleration. By definition, acceleration is the rate of change of velocity. So if the direction is changing, then the velocity is changing. Okay, so the velocity changing means there is an acceleration. Okay, so the direction of the acceleration is directed towards the center of the circle or circular path in which the object is moving. Now in this example, if the object is moving in this circle, the centripetal force and the centripetal acceleration are directed towards the center of the circle. So it's along the radius. Okay, so if I call this the centripetal acceleration A. Okay, so when the object is here, it is directed towards the center of the circle. Let's say here we have the center of the circle. And when the object is here, still it is directed towards the center of the circle. Okay, and by Newton's second law, you know, F is equal to ma, the Newton's second law equation. Mass is constant, acceleration is a vector quantity, force is also a vector quantity. So the direction of the acceleration and the direction of the force are the same. You know, a vector times a scalar or a scalar times a vector is a vector. And the direction of the resulting vector, this vector is the same as the direction of this vector. And it is the resultant force which produces the acceleration, not the other way around. The resultant force produces the acceleration. Okay, so always for an object moving in a circular path or in a circle, the direction of the resultant force is towards the center of that circular path in which the object is moving. And that is the same direction that the acceleration is. So we call this force centripetal force, and we call this acceleration centripetal acceleration. So centripetal force and centripetal acceleration are always towards the center of the circular path in which the object is moving. And you know, according to this equation, F is equal to ma, F has to be a resultant force because the resultant force produces the acceleration. So always centripetal force, okay, centripetal force is always a resultant force. It is a net force, and this force can take the form of other forces. For example, we can consider some examples where one object is orbiting another object. Okay. For example, the sun is orbiting the Earth is orbiting the sun. So the Earth moves in a circular path around the sun. Okay, so there has to be a force which is directed towards the center in which the Earth is moving. So that means towards the sun, and the centripetal force is actually in that case. So let's say this is the Earth, and let's say you have the sun here. The Earth is orbiting the sun. Then the centripetal force is the weight force, the gravitational pull of the sun on the Earth, or the weight of the sun due to the Earth. That is the gravitational pull of the sun on the Earth, and that is the centripetal force. So this is one example. Another example is you can consider any other example where an object is moving in a circle. The electrostatic force of attraction between the nucleus of an atom and its orbiting electron. Okay, so let's say you have you can think of this as an atom, and here we have the nucleus. Okay, the protons are in the nucleus, and here we have an electron which is orbiting the nucleus. Say for example, hydrogen atom, you have one proton and one electron. Now there is a force of attraction between these two particles, and that causes the electron to move in a circle. And the force of attraction is an electrostatic force of attraction. Now, if you consider the electron, the only force acting on that electron is the electrostatic force of attraction between the two charges. Okay, so the proton attracts the electron towards it, and that causes the electron to move in a circle. Okay, so here the centripetal force is the electrostatic force of attraction. So you see, the centripetal force takes different forms of forces. Okay, another example. Let's say we have a vehicle. Okay, so now imagine this is a vehicle. You are looking at it from the top. Okay, you're looking at this car or this vehicle from the top of the vehicle. So you're seeing its roof. Okay, so here let's say the car goes in a circle, or the car moves in a circle. Okay, so here this is the center of the circle, the car is moving, so the car moves in this circular path, and you are seeing it from the top. So you are seeing the roof of the car. This is the top of the roof of the car that you are seeing. Now when the car is moving in a circle, what prevents the car from sliding is the frictional force between the ground and the car. between the tires of the car and the ground. There is a frictional force which prevents the car from sliding when it is going in a circle. Now imagine if a vehicle is trying to move in a circle on a surface which is very slippery, for example an icy road. Okay, so if the vehicle is moving on a road which is very slippery, like let's say for example on ice, the vehicle won't be able to move in this circular path at a certain speed. I mean, at a very low speed it may be able to, but still you might notice that it slips. So the vehicle is trying to move in a circle, but because the friction is very less on that icy surface or icy road, the vehicle, instead of moving in a circle, will try to move at a path which is a tangent to the circle in which it was supposed to move. Okay, but if it was a road which is a rough road, like for example the roads the main roads, okay, no ice, made of tar, there is enough friction to keep the vehicle moving in a circle. Okay, but if the speed is too high, the frictional force may not be enough to maintain this circular motion, and the vehicle could move at a tangent to the original path or tangent to the circle. You remember the radius and the tangent are perpendicular to each other. Okay, a tangent is a line just touching the curve or touching the circle. Okay, so in this example, the centripetal force on the car is the frictional force of attraction between the tires and the surface of the road. Okay, it's actually the frictional force between the tires and the road. And again, that frictional force is directed this way because the vehicle is trying to move that way, and the frictional force keeps it from moving that way and keeps it moving in a circular path. Okay, and there are so many examples. Another example would be something like this. I mean, you would have seen something like this. Okay, so this is a path for a vehicle to move. Okay, and this stuntman, you would have noticed that maybe it's a bike or a car. They move really fast. Let's say there is a car here. Okay, the car moves really fast, and then it can go upside down in this. Okay, and then go all the way there. So let's say let's take the instant the car is here, upside down. Okay, so this is upside down. Now what will happen? There will be two forces acting downwards on the vehicle. One of the forces is its weight. Okay, so there will be a weight force which is acting down like this. Okay, due to gravity, the gravitational pull, also called the weight. And then there will be another force which is the normal contact force. You have learned this in the AS class, you know, the different types of forces. Always the normal contact force is perpendicular to the surface it is exerted from. Normal contact force is also called the normal reaction force or the contact force. Okay, so normal contact force, normal reaction force, contact force, normal force, all mean the same thing. Okay, now this is the circular path in which this car is moving. Okay, it has to move at a certain speed, a very high speed, in order for it to complete this circle, otherwise it will fall down. Okay, now the centripetal force here, I will call it FC. The centripetal force will be equal to the normal contact force N, this one, plus the weight of the object. Okay, now you can see here the centripetal force takes the form of two forces, that is the normal contact force as well as the weight force. Okay, so it can be one force, it can be two forces, it takes different forms of forces, and always remember this is not a force by itself, it has to take the form of another force. And remember also, this is always a resultant force. Centripetal force is a resultant force. Why? Because it produces an acceleration. It is always a resultant force which produces an acceleration. Now in this kind of equation, F is a resultant force. Now if you write this equation for centripetal force, we can call this FC, C for centripetal, is equal to M, okay, the mass of the object, M times A see, AC is the centripetal force. So the centripetal acceleration, AC, the centripetal force produces the centripetal acceleration. Okay, so remember, it's always a resultant force and it takes the form of other forces. It is directed towards the center of the circle, and it is the centripetal force which produces the centripetal acceleration, not the other way around. Okay, then recall and use equations for centripetal acceleration and centripetal force. Now, actually, there are a few equations which you have to remember. I will write them down here. Okay, we have the equation for centripetal. One of the equations for centripetal acceleration is A is equal to V squared over R. So this A is the centripetal acceleration. I'll use a subscript C to indicate that this is centripetal acceleration, and then AC, that is the centripetal acceleration, is also equal to omega squared R. Okay, so this V is the tangential velocity. Now, let's say, for example, in this example here, now the object is moving this way. Okay, so the velocity that is directed at a tangent to the circle, which is this way, is the V. It is the tangential velocity, and this will be the velocity. Say, for example, if suddenly this force is removed. Okay, if this force is suddenly removed, the object will continue at a tangential path to the circle at the moment this force is removed. So, for example, suddenly when the object is in this position, let's say this force is removed, the centripetal force is removed, or it's gone, and then what happens is this object will move at a tangent to the circle, or tangent to that circular path in which it was moving originally. Okay, so it will move this way, and it will move with a velocity V, and we call that velocity tangential velocity. Okay, so that is V, and then R is the radius of the circle in which it is moving. So let's say, for example, here the radius of this circle from here, this is the center, okay, from here to here, that is the radius R. R. Okay, that is the R here, and that is the R here, and we have something here, omega. Okay, it looks like a curly simple W. That is the angular speed or angular velocity. Okay, say, for example, this is moving. Okay, there is another equation for this. We will learn that here. Omega is equal to theta over t. Okay, so this theta, we can say delta theta over delta t. Delta theta over delta t, this is how much of the angle that is covered in a unit time. Okay, so for example, if you consider this circle, okay, initially, okay, so let's say this is the center of the circle, and initially the object was in this position. And object moves to this position. Okay, initially the object was here. After time t, the object moves to, and the angle that it covers during this time is theta. Okay, so I label this angle here, that is theta, and it took a time t to go from here to here. Okay, so the time taken is t. Okay, so that is what we have here. The angle here is in radians. The angle divided by the time it took for the object to cover this angle, the change in the angle in radians divided by the time it took for the angle to be covered is omega. That is what we call the angular displacement. Okay, omega is the angular displacement. You can also label that. Sorry, angular speed. This is the angular displacement. This is the angular speed or angular velocity. So I label this angular displacement. Okay, angular displacement, and this is the angular velocity. Okay, all these equations are extremely important. This one and these two here. Okay, so very important. You have to remember these equations, and it's very simple. See, angular speed, and I will send you this video. Okay, the slides also I will send it to you. Don't worry about it.
Okay.
All right. So here we have this, and omega is the angular velocity or angular speed, because magnitude of velocity is the speed. So some textbooks call this the angular speed. Some textbooks like your one, it says velocity, but the size of this is actually the angular speed. The magnitude or the size of velocity is the speed. Okay, so we have angular displacement, that is how much of the angle it has covered. Okay, this angle theta in a time t. Okay, then you can see this is similar to velocity is what? Displacement over time. Now the what you had learned so far was velocity is equal to displacement, simple s, divided by time. So you see the same equation we are using for circular motion, but in a different way, because here this is in a certain straight line or certain linear direction, but here this is at an angle. So this is at an angular direction. So that's why we have theta here. So it is the angle. Here it is a length. Here it is an angle. So displacement divided by time. So here also what? Angular displacement divided by time. That will give you angular velocity. Okay, this angular velocity is actually in this direction. So it is because it's going in a circle. The angular velocity is also in this direction. Okay, so it is this way, omega. Okay. Even here also we can label v is always tangential. Okay, it is at a tangent to the circle, but omega is that way. Okay, it's along that circular path. Okay, so that is the difference between v and omega. Omega is along that circular path. V is at a tangent to the circular path. It makes a angle of 90 degrees between that radius of the circle with the radius of the circle, or with the angular direction of angular acceleration. Sorry, centripetal acceleration. Okay, so you should know these two equations. Now we can apply this to F is equal to ma. Okay, so you see Fc is equal to mac. Okay, so if I apply to this, what I will get is the centripetal force Fc is equal to m. Okay, so for a, see, I can substitute this. So mv squared over r. And also, now the centripetal acceleration is equal to this. So also we can say the centripetal force is equal to m omega squared r. Okay, so these are the important equations. Now you know how to derive this equation using this. And I also showed you how to relate this to this one. Okay, and I also showed you the diagram. And you should know how to label all these things. Okay, this is in radians per second. And here this is in newtons. And these all of these have the normal SI units. Okay, the ones you already know. This is in kilograms. This is in meters per second, this is in meters, and that will give the centripetal force in newtons. Here, again, kilograms. Now, this will be in radians per second, because this is in radians, this is in seconds. So, this will be in radians per second, and R is in meters. Okay, then we'll continue. So, these are the, here I have taught you the important things that you need to know in order to do almost any of these questions. Okay, so recall and use equations for centripetal acceleration. That is what I taught you just now. Okay, now we will move on to the actual chapter. Okay, so here, okay, here you see the angle, what I explained before. And you see here the meanings of these are all given in the glossary. Okay, angular displacement, you can refer it at the back of the book. The definition is given in the glossary. And I told you what the angular displacement is already. Okay, so that is in this example, it is theta, how much of the angle it covers. Okay, theta. Okay, so you see there are some questions, you can do this. Okay, now we will learn how to convert from radians to degrees and degrees to radians. A very easy way of doing this is to remember that pi radians is equal to 180 degrees. Okay, so if you remember this, you can do almost any conversion involving, you can do any conversion involving radians and degrees. Okay, so radians we write a small c sometimes, so that is what we call radian. This is kind of to indicate that it is in radians, or we can also write it without the pi, without the c, so just the pi. And also another way of expressing that the angle is in radians is to write RAD, in short for radians, RAD. So all of this means the angle is in radians. Now if you don't write anything also, see nothing is written here, but that means it is in radians. Okay, so for example, if you get something like 5, if you write 5.2 or 5, and if you don't write anything, that means that is in radians. But if something is in degrees, you must write the unit. That small zero like thing you write for the unit of degree. So that has to be written. But when it is radians, it is not necessary to write this C or this RAD, meaning indicating radians. If there was no unit to be seen or nothing to be seen there, that means it is in radians. Okay, so we can write pi radians is equal to 180 degrees. Okay, so with this you can do any conversion. So if it's 2 pi radians, then the angle will be 360 degrees. And if it is 90 degrees, you have to divide this by 2, right? So 90 degrees is pi divided by 2 radians. Okay, let's consider the quadrants. You have the first, second, third, and fourth quadrants. I will draw that. So let's say we have the quadrants here. Okay, so this is the y-axis. Here we have the x-axis. And let's say the angle here, from here to here, the angle is 90 degrees. Okay, then from here to here, the angle is 180 degrees. And if you go all the way around, from there to there, that is 360 degrees. 360 degrees, which is 2 pi radians. 2 pi radians. Okay, so you see from here to here, that is 90 degrees. 90 degrees is pi divided by 2 radians. So in order to do the conversion, if you remember this, that is sufficient. Then you can convert from degrees to radians and radians to degrees. And there are some questions over here in this chapter where you have to convert between radians and degrees. Now can you see here, 360 degrees is 2 pi radian. So if you want to find for 1 radian, 360 divided by 2 pi into 1 radian. Okay, and there is also a formula for radian. We'll write that also here, and it is given here. You see here, angle in radians is arc, length of arc divided by the radius. So you see that here, the angle in radians, that is, let's say theta. Okay, theta in radians is equal to, you see here, theta in radians is equal to S divided by R. S is the arc length and R is the radius. So the arc length divided by the radius is equal to the angle in radians. We can also say S is equal to R theta. S is equal to, when you rearrange this, arc length is the radius times the angle in radians. Okay, so you have to remember this formula of how you can find the angle in radians when you know the arc length and the radius. Okay, so the arc length divided by the radius is the angle in radians. I'll write that also here, or I can use a new page. Okay, so let's say we have a circle. And say this is the center of the circle, and let's say from here to here, this angle is, let's say, theta, and then okay, so this angle is theta, and then let's say this arc length from here to here, let's say that is S. In the maths textbook they call this L. Okay, now we will use S here because it's a displacement. Okay, so let's see, L, theta, and then R. Okay, the angle in radians, theta, is equal to the length of the arc S divided by the radius of the circle or circular path. That is the equation. Okay, so you should know this, and also you should know how to convert from degrees to radians and radians to degrees. Now can you see they have defined what the radian is. Okay, 1 radian is the angle subtended at the center of a circle by an arc length equal to the radius of the circle. 1 radian. So when you get 1 radian when the arc length is 1 and the radius is 1. Okay, 1 radian is the angle subtended at the center of a circle by an arc of length equal to 1 radian, equal to the radius of the circle. So here, sorry, this is 1. The unit here should be the same as the unit here. So if the length of the arc is equal to the radius of the circle, then the angle is 1 radian. Okay, now this is what I showed you. 2 pi over 360 degrees is equal to pi over 180. So if you remember this, you can do the conversion from degrees to radians and radians to degrees. Okay, one more thing here. You see this circumference divided by the radius. Okay, so how we get this 2 pi? Now 360 degrees, I showed you here, 360 degrees, 360, you go all the way around. That is 2 pi radians. Okay, so from here to here, 180 degrees is pi radians, 360 degrees is 2 pi. Now let's see how we get that. Okay, using this. Okay, if the angle is say 360 degrees, okay, that means you go all the way around. You go all the way around. Now what is the length then? What is the length? Okay, so we'll write for 1 full circle. Okay, so for 1 full circle, what is the what is this length all the way around the circle? What is it called? Circumference. Okay, so if you go all the way around, that is the circumference of the circle, and the equation for circumference of the circle is 2 pi r. 2 pi r. Okay, so this is the circumference of the circle divided by the radius of the circle. All right, so we are using this formula. So circumference divided by the radius will give you the angle in radians. So when it completes 1 full circle, the angle is 2 pi radians. So let's say it started here, it went all the way around here. So the angle that it covers in radians is 2 pi. Okay, also we can consider for half a circle. For half a circle. For half a circle, the angle then will be, half a circle means half of the circumference. So that is what? 2 pi r divided by 2, which is pi r. Okay, so the circumference is half the S is half the circumference. So circumference divided by the radius of the circle, that will be pi. Okay, so here we are getting the angle in both cases. Okay, we are getting the angle in radians. Okay. Okay, so I mean, see, this is a very easy example. They have given the angle in degrees and they're asking what is it in radians. Okay, so you can use that relationship. 180 degrees is pi or 360 degrees is 2 pi. One of these you can use and then get the answer. Now the angle given is 60 degrees. So 60 degrees means we have to write this as a fraction so that the degree is in the denominator. So it will be pi divided by 180 degrees into 60 degrees. Okay, pi divided by 180 into 60. So degree cancels, you get the answer in radians. Usually we express radians in terms of pi, but also you can write it like this. Okay, so pi divided by 3. For mathematics, you would have learned pi divided by 3 in radians is 60 degrees. Okay, then this is what I explained before about angular velocity, angular speed, angular displacement. You see this equation which I explained before? That is this one. Angular velocity is equal to angular taken, and I showed you what angular displacement is. Okay, so that is how much of the angle that is swept in a unit time. Okay, then that divided angular velocity. So angular displacement is how much of the angle is swept, and that divided by the time for the angle to be swept is the angular velocity. And the angle we give here in radians. Okay, so then the unit of angular velocity will be radians per second. Okay, so there are questions there which we can do. Then we have another equation here, V equals omega r. Okay, this is another equation, V equals omega r. We'll write that also here. So we have the speed. Okay, this is also called the tangential speed or tangential velocity equals omega r. So in your book they just say velocity. So actually it is referring to that tangential velocity. Okay, you remember what the tangential velocity was? It is this velocity. It is at a tangent to the circle, so we call it tangential velocity. Okay, tangential velocity or tangential speed. Okay, so here they say speed, but when they say speed they are referring to that. Okay, the tangential speed or tangential velocity is equal to omega r. Okay, so we have the speed is equal to omega is angular speed or angular velocity. Okay, equals angular speed times the radius of that circular path or radius of the circle in which the object is moving. Circle or circular path the object is moving. Okay, then there is an example. Okay, by the way, this was also another example that I wanted to tell you of circular motion. Now you see here the child is making this object moving in a circle. So this is something a bit heavy, maybe something like a stone, and then maybe this is a string. Okay, so you can cause this motion. Now this is moving in a circle, and I told you the centripetal force takes different forms. So in this case the centripetal force is tension, is the tension in the string. Okay, so here is another example of circular motion, and let's say she let go suddenly. If she releases this suddenly, the tension is gone. Then the object will continue to move at a tangent to the circle. So let's say she releases it at this moment. She releases it at this moment. Now this is moving in an anti-clockwise direction when you look from the top. Okay, so if she releases this, it will move at a tangent to this circle. Okay, at this moment, so let's say this is the radius, so it will be the velocity v or the speed v will be in this direction. So it will move in this direction at a tangent to the path that it was moving at the moment the string or the tension is removed. Okay, so here is an example of where you have to use that v equals omega r. Let's go through this one. A toy train travels around a circular track of radius 2.5 meters in a time of 40 seconds. What is its speed? What is its speed? So speed means the tangential speed or the tangential velocity. You have to find the magnitude of the tangential velocity. Okay, so they have given us the radius and they have given us the time, and we are supposed to find the speed. Okay, one way of doing this is you can use this equation, omega equals 2 pi over 40. Omega is what? The angular speed. Okay, so first we can find the angular speed. They are using that equation around a circular. So calculate the train's angular velocity. One circuit of the track is equal to 2 pi radians. The train travels around in 10 seconds. Therefore, so we get this. Okay, so 2 pi radians, and we divide by 40, and so you get this angular speed in radians per second. Okay, then we use v equals omega r. We have the angular speed and we know the radius that is given. Okay, so here we know that they say circular track of radius travels around a circular track of radius. So that means for one whole circle it takes 40 seconds. So 2 pi. So again we are using that equation here. This equation. Okay, this is what is used. Okay, so it completes one whole circle. Now the angle for one whole circle is 360 degrees or 2 pi radians. So here they substitute 2 pi and the time taken for that is 40 seconds. So that's how they get this 2 pi divided by 40. Okay, so they get the this velocity. Okay, that for it to move in that circular path, the angular speed or angular velocity, and then to convert from angular velocity to tangential velocity, we use this formula. Okay, so we know this and we know the radius, so we get the tangential speed or the speed. Okay, so this is one way, and there is another way. You could have arrived at the same answer by calculating the distance traveled, that is the circumference of the circle, and dividing it by the time taken. Okay, so here we are using actually this equation. Okay, for the second method we can use this. We can calculate the distance traveled, that is the circumference, 2 pi r, and divide by the time taken. Right, so two ways of getting the same answer. Okay, and you can see that if you put these two together, say for example here we for omega we substitute this 2 pi over this, so then what do you get? 2 pi r over t. Okay, again you will also learn that omega v is equal to 2 pi r over t. Okay, I will show you what they are meaning. So what they mean is this. Now the tangential speed v is equal to, now for one whole circle, for it to go one whole circle, the distance traveled is, okay, I'm going to use this one, this equation. Okay, so I will write it here. Velocity is equal to the displacement divided by the time. Now the displacement for one whole circle, when you go all the way around, okay, so let's consider this. Okay, so going from here to here, so let's consider as 2 pi r. Okay, so that is the distance. Okay, so to consider this as speed is distance over time. Then the time is for one whole round, the time is the period, capital T. Okay, so 2 pi r over t is v, the speed, because if it's velocity, then it comes back to the same point, it is 0. Okay, so here we consider it as the speed. So 2 pi r over t, you can see when you do that, so 2 pi over t is in this case this one, omega, and r is this, so v equals omega r. Okay, so 2 pi over t, when you rearrange this equation for 2 pi over t, if you substitute omega, you will get r, because this is the angle it sweeps, and the angle it sweeps in a time t, that is what omega equals delta theta, or theta divided by t. All right, so if you use this also, you will get it. You find the circumference, and then the time to complete that circumference, capital T. Any questions?
No, sir.
Okay. Okay, then here are some more examples they are giving you. Okay, the Earth is orbiting the sun, and the centripetal force in this example is the gravitational force of the sun. And can you see here the tangential velocity, which they call the speed in this book?
Yeah.
Okay, so if this force is suddenly removed, the Earth will move in this direction with this velocity, because there is no resultant force there. So this is the only force acting on this. So if suddenly this force is removed, then there is no force acting on the Earth. So it will move in a straight line with this velocity. Newton's first law. And here they explain the vector diagram. Okay, so that is the change in velocity. You can see here when it goes from here to here, the change in velocity is this. So you draw the vector triangle, and then after that you can get this. Then acceleration at a steady speed. I told you when the speed is constant, if the object is moving in a circle, even though the magnitude of velocity is constant, that is the speed is constant, the direction is always changing, so there is still an acceleration, because velocity is a vector quantity, so velocity is changing. That means there is an acceleration, and that acceleration we call centripetal acceleration. Okay, then here you see a diagram of something that is shot. Okay, we can also apply this for a satellite. Okay, so now if something is shot very fast, okay, so it's better if you consider this example of like releasing a satellite. So you go to outer space, and then we have, let's say, releasing a satellite, and if we release the satellite too fast, it will go out of the orbit of the Earth. If it is too slow, it will fall onto the Earth, and if it is the right amount of speed, then the object will continue to move in a circle. Okay, so two things can actually happen to an object that has a resultant force on it. Okay, so if an object has a resultant force acting on it, then the object will fall towards the object that is causing that resultant force, or the object has to orbit the other object. Again, if you consider this example, two things can happen. Now you see there is a resultant force on the sun. So two things can happen. One is the two objects should come towards each other. That means the Earth should fall towards the sun, or it should go in an orbit around the sun. These are the two things. So in this case, it's orbiting. Okay, so I showed you this equation for centripetal acceleration. All right, then I showed you this equation for centripetal force. Okay, I wrote this down earlier. Using Newton's second law, F equals ma, we can get the centripetal force. Okay, then here is an example. So actually you have to use these equations to do certain calculations like this, for example. Okay, Now, for example, if it is something like the Earth orbiting the Sun, or maybe a satellite orbiting the Sun, so a satellite orbiting the Earth. Okay, so if you consider a satellite orbiting the Earth, the weight of the satellite is mg. The weight of the satellite is mg, or then that is the weight of the satellite is the centripetal force on the satellite, and that is equal to mv squared over r. Okay, so the centripetal force, I will show you another step here. Let's say we have a satellite orbiting the Earth. Okay, so this example is similar to that. Okay, so let's say this is the Earth, and then here let's say we have a satellite. All right, so the satellite is orbiting the Earth. So let's say it moves, takes a circular path like this. It goes like that, and it goes around. Right. So imagine, okay, it's going in a circle. Okay, it goes in this path, and then it comes back, something like that. Yes. Oh yeah, that's better. All right. Now there is a centripetal force acting on this because it is moving in a circle. So anything moving in a circle should have a centripetal force, and the centripetal force is actually the weight of the satellite due to the Earth. Okay, so you remember the equation for centripetal force, that is equal to mv squared over r, also m omega squared r. Okay, so this is, here we have the radius of the circle, so from here to here, that is the radius of the circle, and then here we have the angular speed omega, and if it is moving this way, the angular speed that way, then the what do you call the tangential speed, or in simple terms of the speed is that way. Radius we know, the m is the mass of the satellite. Okay, the mass is constant, wherever it is, the mass is constant, but the weight changes from place to place. Okay, so in this case, the centripetal force is the weight of the satellite due to the Earth. So that is mg, mass of the satellite, times the gravitational field strength. That is equal to mv squared over r, and also we can say it is equal to m omega squared r. Okay, so if you use these two equations like this, then the mass cancels out. Even if you use these two also, the mass cancels out. So we get the gravitational field strength as v squared over r. Now we remember that equation for acceleration. Acceleration is equal to, the centripetal acceleration is equal to v squared over r, and also omega squared r. Omega squared r, and that is what we have here. Now in this case, the acceleration is what? The acceleration due to the weight, and that is what we call gravitational acceleration, or the acceleration of free fall. So this is also the now the weight force. So the acceleration it causes, the centripetal acceleration in this case will be the acceleration of free fall for this example. Okay, also we can say it is omega squared r, and they are calculating the velocity that this satellite should be at. Now in the previous explanation, you saw that I told you that the satellite should be released at a certain speed. If the speed is too high, it will go out of the Earth's gravitational field. It will go out of the orbit. If the speed is too low, it will fall onto the Earth. So here we are actually doing this to find the speed at which the satellite should be released or sent, so that it continues in an orbit around the Earth. And to do that, we have to do this process, and we can find v. Now we know that we can find the, let's say we know the gravitational field strength at this height, so we substitute that, and also we know the radius from the center of the Earth to the center of the satellite r. Then we can find the tangential velocity, that is the speed at which we have to release the satellite so that it continues in an orbit around the Earth. Okay, so you can see that substitution there in the book. Okay, so we have v squared over r, and then we get this. So v squared, r is the radius. It should be the other way around, right? The square root should not be here. This step is fine. Here this step is okay if the square root is not there. Okay. And here they are telling you, now this is a different example. So this is an object that is close to the Earth's surface. Okay, so that's why they have substituted the radius of the Earth here. But here I was talking about a satellite. So in this one, if something is close to the surface of the Earth, in order to make it go around the Earth in an orbit, they are finding what the speed should be. So the speed of the object should be this much. Thus, if you were to throw or hit a ball horizontally at almost 8 kilometers per second, so this is about 8 kilometers per second, it would go into orbit around the Earth. Any questions?
No, sir.
All right. Then you see the origins of the centripetal force. Already I explained this. See the example of the car. A car cornering on a level road. So that means the car is going in a circle. You know, if it takes a bend around a corner, then it moves in a circular path. Okay, so there the centripetal force is the frictional force between the tires and the road. And the frictional force is always parallel to the two surfaces. So the frictional force is between the tire and the road, and so it is always parallel to those two surfaces. Remember, these frictional forces are always parallel to the two surfaces, whereas the normal contact force is always perpendicular to the force it is exerted from. And one more thing, the weight is always vertically downwards towards the center of the Earth. Okay, then there are more questions. We can do this. Okay, one page is missing. Rather, 2 pages. Okay, no, 1 page. Okay, but that is also very simple. Not much, nothing much complicated. Actually, the page that is missing is giving you some examples of what I told you before. Okay, and if you refer your book, you can see that.
Yeah.
Okay, the page that is missing, page 266. If you refer your book, you can find it. There is an example of a vehicle that is going in a circle. Now, you know, if you consider these racing tracks, you would have seen the racers. The racing tracks, you would have noticed that the road is banked. Banked means the road is at an angle where the vehicles go in circles. Okay, if you have played certain computer games like Need for Speed, you would have seen that where, you know, you have these racing tracks which are something like this. For the cars, you have this. Okay, for the cars, let's say this is a racing track, and when because these cars are moving at very high speeds, the road here is banked, meaning it's not horizontal. The road is not flat, but it is curved like this, so that you know it's kind of like curved like that. You understand? Also, if you so I mean, you even in these theme parks, you know, we have these water slides. So when you go on those water slides, have you seen that that is also curved like this? It is not flat, because if it's flat, you may fall out, or you may hit the top of it. It is curved like this. So the vehicle comes like this, and then it is going like that along this curved path, which is not horizontal. Okay, the reason for that, so we call that the road is banked. Okay, so let's say we have a vehicle. Okay, it is in your that kind of diagram is in your book. Okay, so let's say this is the vehicle, we are seeing it from the back. Okay, so this is the back of the vehicle that we are seeing, and the tires are like this. Okay, so this is the back of the vehicle that we are seeing. Okay, so let's say these are the tires. Now the vehicle is moving into the page. Okay, because we are seeing it from the back, and this is the road that is banked. The rod is at an angle. It's not horizontal, but it is at an angle. Now in this question, in this example, let's say the weight is vertically downwards. Okay, the weight is vertically downwards. And then we have another force, which is the normal contact force. Okay, so the normal contact force is exerted from the places where the vehicle is in contact with the ground. Okay, but for simplicity, I will just draw it like this. Okay, otherwise I will have to draw each force, one force here, one force here. So the combined normal contact force, I will draw it like that. Okay, so N there, normal contact force. It is exerted from the points where the object is in contact with the ground. Okay, and this car is moving in a circle. So if it is moving in a circle, the centripetal force, so it's moving into the page. Okay, so it's moving along this. So let's say it is somewhere like here. Okay, maybe moving like yeah, moving from it. So it's coming this way. Okay, it's coming this way, and we are seeing it from this side. This is the eye. Okay, we are seeing it from the car, and it is moving in this part, in this direction. Okay, so since it's moving into the page, so we are seeing it from this side, it's moving this way. The resultant force is this way. That is the centripetal acceleration. So let's say it's moving at a constant speed. For example, now we are actually supposed to find the centripetal force here. So the centripetal force is in this direction. Okay, the acceleration, the centripetal acceleration is in this direction. So therefore the centripetal force is also in this direction. Now in order to find that, we will have to resolve the forces. Let's say the angle here is theta. Now do you remember in M1 you did some questions where the objects were in an inclined plane?
Yeah.
Okay, let's say this is the angle theta. Then with this, okay, the angle here will also be theta. You know, the reason is here this angle is okay, this, if you consider this triangle, this is 90, so this will be 90 minus this value. This angle here is 90 minus this value, because this is a right angle triangle. Then again, to find this angle, the angle here between this and this, that is also 90. So again you do 90 minus that. So that's why this angle is equal to this one. Okay, in M1 you have plenty of questions which are like this. Okay, so if you want to find the component of the weight this way, that is down the plane, sorry, rather perpendicular. Yeah, so if you want to find the component of the weight down the plane, what do you do? W sine theta. Okay, by the way, there is also a frictional force. If the vehicle is moving very fast, then the frictional force will be down the plane. If it is moving quite slow, then the frictional force will be up the plane. Okay, so there is also a frictional force. Let's say the vehicle is moving not that fast. Okay, it is moving at a certain speed, which is vehicle will tend to slide this way. Okay, do you get it? If the vehicle is moving very fast, the vehicle tends to skid this way, tends to move this way. But if the vehicle is not moving that fast, the frictional force prevents it from sliding down. So the frictional force is, let's say, this way. It depends on the speed also. Okay, speed too high means it will try to go that way, then the frictional force will be downwards when it's trying to go up. But if the speed is not that high, if it's low, then the frictional force will be this way, preventing the vehicle from sliding down this road. Okay, so we'll call this the frictional force. Okay, then okay, so if there was friction, now to get the centripetal acceleration and the centripetal force, we'll assume, to make things easier, we'll assume that there was no friction here. All right. Yeah, we can assume there was no. Okay, so let's consider this. Or even if there was friction also, that is also okay. So let's say now, if I draw this line here, that is a vertical line. Okay, so it is in the line of action of the weight force. Okay, so if I draw that vertical line, then this angle here will also be theta, because they are vertically opposite angles. Okay, this angle here is also theta, vertically opposite angles. Okay, now there is no motion in this direction. The vehicle is not moving in this direction. Okay, so what that means is n cosine theta should be equal to W, because the vehicle is not moving vertically. So then the vertical components of forces are balanced. So we can say n cosine theta. That means if you take the component of this reaction force, which is perpendicular to the surface, n cosine theta should be equal to the weight of the object. Then if you consider this direction, then n sine theta. N sine theta, again, it is not moving in that direction, but n sine theta, but there is a resultant force that way. So this n sine theta is what provides the centripetal force. Okay, so n sine theta is equal to the Fc. Okay, you know the centripetal force is this way. It is in the direction of the acceleration. So that is equal to this one. So we can say also equals mv squared over r. Okay, so this is another equation we can get. So n sine theta. Now you see, if you resolve the weight force in this direction, the weight force has no effect because it is perpendicular to this direction. So the weight is downward. If you take the component of the weight this way, it is W cosine or sine 9. Yeah, so if you take it this way, the angle here is 90 degrees. So W cosine 90 is 0. Cosine 90 is 0. So the weight has no effect in the in this direction. So it doesn't take part in the centripetal force, but this has an effect. Okay. So if you take it this way, then it has some effect there. Okay. So n cosine theta is equal to the weight of the object, which is mg. Then n sine theta is equal to the centripetal force. Okay, so let's assume there is no friction. Okay, so assuming there is no friction, because if there is friction, then this force also comes into this equation. All right, so to make things easier, we'll assume there is no friction, then you get these two equations. Okay, then there are some more examples given in your book in that particular page, which is missing in this electronic book. Another one is they have an aeroplane. Okay, so you have an aeroplane. It's a different color. There is an aeroplane. Okay, so let's say this is the aeroplane. Okay, the aeroplane. And yeah, these are the two wings of the aeroplane. Okay, so this is that top part. Okay, so this is the front. So we are seeing the aeroplane from the back. Okay, so these are the two wings of the aeroplane. Then we have this. This is the front of the aeroplane. Okay, so now the aeroplane is also moving at an angle. Okay, so let's say this is the vertical direction, and the aeroplane is moving this way. Okay, so the weight is vertically downwards. So I will draw the weight force. The weight force W equals mg. Mg. Then we have a certain force. Now there is a force on the wings. Okay, the air exerts, when it's moving this way, the air exerts a force on the wings. So the force on the wings is perpendicular to the wings. Okay, so let's say here I have the wings, so I will draw it perpendicular to the wings. Okay, we call that the lift force. Okay, so this causes, now let's say the aeroplane is moving in this direction. Okay, so the component of the so I will also label this. Okay, so the component of the lift force in the vertical direction will be equal to the weight if it is neither moving up nor down. So let's say the aeroplane is moving in a circle at a constant height. So it's at a constant height and it is moving in a circle. Okay, so when it is moving at a constant height, the lift force which is in the vertical direction. Okay, so we'll resolve the forces vertically. L cosine theta should be equal to the weight. Then L sine theta is in the direction of the center of the circle. So L sine theta will be equal to the centripetal force Fc. Okay, so this, if you L cosine theta is the component of L in the vertical direction, that is equal to the weight. Then L sine theta is in this direction. Okay, it is in the direction of the circular path, center of the circular path in which the object is moving. So which is the same direction as the centripetal force. Okay, so the centripetal force is then equal to L sine theta. Any questions?
No.
Can you visualize it?
Yes, sir.
Yes. Okay. Then so that is A in the diagram. Okay, for the fifth example. Okay. Then there's another one where you have the a tension in a thread. Okay, so it's very similar to this one. Then in the amusement parks, you have something like this. A picture is given. Okay, and there is a child inside this. Okay, and this thing go. Let's say the child is here. Okay, so the child is not attached to the wall, but because this is rotating at a very high speed, then because it is moving, so it's a omega, this thing the child is in, so the child just sits there or stands there and just puts something there, and but he's not fixed to the wall, but because this is moving at a very high speed, this is rotating. Okay, so you see this will rotate. I mean, it's rotating at a very high speed. Then what will happen is so first we'll label the forces. So there will be a normal contact force this way, and the weight of the child is this way. Okay, this you get this in certain amusement parks this way, and then we have what we call the frictional force. Okay, the frictional force is this way, the force of friction. Okay, so what happens is when the normal contact force increases, the faster it moves, the greater the centripetal force. Now in this case, the centripetal force is equal to the normal contact force, and also you know centripetal force is m omega squared r or mv squared over r. Okay, so what happens is when this omega square, that is the angular speed or the tangential speed, when that increases, what happens is the normal contact force or the centripetal force in this example increases. Okay, so when the centripetal force increases or the normal contact force increases, then also the frictional force increases. Okay, in the M1 class you would have learned F is equal to mu r. Okay, if you haven't learned it, I'll say it now. Okay, or F is mu r is the normal contact force. Okay, or we can write mu n because of this example. So when the F is the frictional force, this frictional force here. So when the frictional force F increases, when this increases, mu is a constant. Okay, it depends on the nature of the two surfaces. Mu is constant. Then what happens? When it's the other way around. When n increases, the frictional force increases. Okay, so when the n increases, this is a constant. It depends on the nature of the surfaces. So when this increases, the frictional force increases. So it will come to a point where the frictional force can balance the weight. Okay, so the faster this rotates, the greater will be the normal contact force, because when omega or v increases, n increases. So when n increases, the centripetal force increases, or the normal, when the normal contact force increases, when the centripetal force increases, the normal contact force increases, n increases. So according to this equation, when n increases, the frictional force increases. So it will be sufficient to balance the weight. Now if the speed was, let's say, 0, if the speed was 0, then the centripetal force is 0, then there is no normal contact force. So if that means this decreases and becomes 0, then there is no frictional force. So then the child can't be, I mean, he can't then lean on the wall like this. He will fall down. Okay, so when the speed decreases, this frictional force decreases because the centripetal force or M decreases, and then it's not enough to balance the weight, so the child will fall down. So that means there should be a minimum speed that it should be rotating in order for the child to be just leaning to the wall and not falling down. Okay, and also earlier I explained this example here. You see, in this example, the frictional force, the centripetal force is the weight plus the normal contact force. Now, you can get a question like this in the exam. Okay, I've seen it in the past paper, so we'll try to work this also out. Now, in this question, the weight is constant. Okay, the weight doesn't change because that is equal to mg. So the weight is, so it is referring to this example here. Okay, when the car is in the upside down position, it is moving in a vertical circle like this. So the weight is constant. So the frictional force depends on the speed I told you. Okay, and if the normal contact force is 0, that means that is the minimum. We can get the minimum speed there. Okay, so this is equal to mv squared over r. So I will write that here. N plus W. Now W is constant, and for centripetal force we can have m v squared over r. Okay, so let's say it is moving in this path, and at this moment v is this way. Okay, so we have mv squared over r, and r is the radius of this circular path. Now you can see here, if this becomes when v increases, what happens? When v increases, now m and r are constant. Okay, so the r radius of the circle is constant. When v increases, yeah, this centripetal force increases, and this is constant, therefore the normal contact force increases. And same thing the other way around. When this speed decreases, the normal contact force decreases. Okay, so the normal contact force, there has to be a value there, because then only these two are in contact. Now if the speed is too low, what happens? The normal contact force can become 0. If it becomes 0, then this falls. The larger this is, the greater the contact with the ground upside down. When n increases, now the faster you go, now you can think of it in reality. Okay, so imagine you are in this car. The faster you move, what will happen? The greater the car will be fixated to the ground. Do you get it? The faster you go, there will be a greater n. The normal contact force will be greater because the car pushes down to the ground. The faster it goes, you can think it pushes down upside down this way. Okay, then the more it presses down onto the surface, the greater will be the normal contact force. So when the speed increases, the centripetal force increases, so therefore the normal contact force increases. Now if the normal contact force is less, there will be less contact with the ground, and then the vehicle can fall down. So this way, if you set n to 0, then you can find the minimum speed at which the vehicle should pass this path in order to complete the circle without falling. Okay, so the minimum value n can have is 0, just loses contact with the ground. Okay, so there was a past paper question where you had to find this v, and to do that you had to write this equation. The centripetal force is the normal contact force plus the weight, and then you know the mass r is given, so you have to find v. So to do that, you have to set n to 0, and then you will get the minimum tangential speed, or the minimum speed that the vehicle should have at this position, so that it completes the circle. Any questions on that? Any questions?
No, sir, no.
Okay. All right, then we'll go back to the book. So that was the last part. All right, last part. And now let's check the summary. Yeah, so summary of everything. Now you should be able to do all these questions now. Remember those equations, you may have to use them again and again. Yeah, so this is the summary of what we learned so far. Okay, the equations are also given here. This equation, this one, and there was another equation, V equals omega r. Okay, it's also given. So these are the important equations that you should know. Okay, so first thing is you should know how to convert from radians to degrees and degrees to radians, and the definition of radian. Okay, theta equals s over r. Arc length divided by the radius will give you the angle in radians. Okay,
Yes.
so you should know how to convert from degrees to radians. You can remember pi radians is equal to 180 degrees. An object moving at a steady speed along a circular path has uniform circular motion. So the speed is constant, but since it's moving in a circle, there will be a acceleration towards the center of the circle, which we call the centripetal acceleration, and it is the centripetal force which produces the centripetal acceleration, not the other way around. The angular displacement theta is a measure of the angle through which an object moves in a circle. Now you saw that earlier, how much of the angle it sweeps when it goes like this. That is the angular displacement. We use the symbol theta for that, and the unit is in radians. Then angular velocity, you know, this is the equation, theta divided by t. Angular displacement divided by the time. Change in angular displacement divided by the time taken. And then you can use this equation to convert between tangential speed and angular speed. Okay, V equals omega r. For an object moving with uniform circular motion, speed and angular velocity are related by this equation. An object moving in a circle is not in equilibrium, because if something is in equilibrium, the resultant force should be zero. Now, for something moving in a circle, the resultant force is not zero, because there is a centripetal force, and centripetal force is always a unbalanced force. It is always a resultant force. Okay, so it has a resultant force acting on it. The resultant force acting on an object moving in a circle is called the centripetal force. This force is directed towards the center of the circle and is at right angles to the velocity of the object. Now you saw the tangential velocity. So the tangential velocity and the tangential velocity and the acceleration are perpendicular to each other. So you see here, this is the velocity or speed, and this is the acceleration here. So they make an angle of 90 degrees. The resultant force and the acceleration are in the same direction. Okay, then we have this equation, a equals v squared over r, and a equals omega squared r, or r omega squared. You should remember this, and I told you how to get it using f equals ma. If we substitute for a, we get this equation, these equations, and this is for the centripetal force. Okay, any questions then?
Yes, sir.
Okay, so you have to do all the questions in these brown boxes here. The solutions are also given here. Okay, so if there are any questions, then you can ask me, and we can also discuss some of these questions. Any doubts you have, you should be able to do the questions. If there is any doubt, just refer the part before the questions.
Yes.
So the questions here are based on what is taught here, for example. So if you have a doubt, you can refer this. Anyway, it will be very easy because I already explained it to you.
Yeah.
Okay, so all right then. Okay, all right then. Any other questions?
Yes, sir.